It's very related to the previous one, in the sense of we are using also self-sensing concrete, self-sensing cementitious materials, and also 3D printing. But now we are going to explore the different printing paths, as well as, not mentioned here, but also the types of material that we are going to use. Presently, briefly here, a mortar and a paste, as I will show. So I will not spend a lot of time on this because it's very similar to the previous one, but what I just reinforcing that the self-sensing concrete is mainly this material where this concrete that we can use as a sensor, so we can get some electrical response that can be used to evaluate let's say the mechanical behavior of this structure under the variation of electrical pulse, let's say, with a correct type of measurement that we perform. So 3D printing concrete. Now I will enter deeper in this part that I didn't mention a lot in the previous one, but 3D printed concrete is this manufacture method that is quite powerful, especially in these days. There is a growth, especially in the literature, in terms of this type of manufacturing processes in the last years, very recently, I would say. Also, we are starting to see some types of production of actual buildings and bridges as well, small bridges. And this type of manufacturing process has some advantages, direct advantages, when we compare to the traditional ones. And here I would like to mention the less waste, also safer sites, because we are using also a reduced workforce as well as a reduced amount of work form. And also, as I mentioned previously, we now can explore different geometries that can be quite useful, both in terms of structural applicability and also in terms of self-sensing capacity. And this small video showing printing that we did recently in Iowa State University. But what I would like to mention here is that this 3D printed concrete has also an interesting property. That is the possibility to orientate the fibers, the fillers inside of the nozzle during the printing process. So this can be a useful property for us, especially when we are talking about self-sensing concrete. As I mentioned earlier today, we want mainly to form some conductive paths that can be used to establish this contact as well and increase the piezoresistive performance of our material, which allows us to use it as a sensor. This is mainly one of the main, let's say, properties that conducted this, that allow us to go deeper in this topic of exploring different printing paths, because now we can sort of study how the printing path is going to affect, in fact, the sensitivity and the response of our printing elements. But I would like also to mention some limitations of this technology that is mainly attributed to the anisotropic behavior of this material, since now we are talking about layer deposition. Mainly we are also creating these regions more fragile, that has increased presence of voids, for example. And also, the durability of this type of technology is not so well explored yet, since it's a quite recently technology. There is a lot of knowledge that we need to go deeper and try to understand in this sense. And also the lack of standardization, because both for processes, materials, and regulations, because this is also one, let's say, one issue that affects the dissemination and scalability of this type of processes. With this in mind, the objective of this presentation now is to show some of our developments in terms of exploring different printing paths and sensitivity of this cement-based material, 3D printed cement-based material. So the process here was quite similar to the previous one. Mainly, we mixed the dry materials in order to get to a point of homogenization and dispersion. This time we didn't use the hybrid composition, but only the chopped carbon fibers that are the long carbon fibers with 6 millimeter length. We also added the water in 2 different steps, as I mentioned, and we used a different printer this time. And we printed samples with these geometries, where we first printed one with the longitudinal printing path, with the printing path, in fact, parallel to the longitudinal axis, and the other one we printed with the printing path perpendicular to the longitudinal axis. And I am going to refer in this work to this first sample as a longitudinal one, and this one as a transverse one. Also mentioned here that we printed a mortar in this geometry, as well as a paste for the perpendicular geometry, the transverse geometry. So, not going deeper on this, but first regarding the test setup, we mainly perform a similar approach as we performed before, but with this time using also a universal test machine with a 3-point bending test. This time now we used a biphasic approach, not the LCR as we used before. And we use basically a PXI with PXI model to get the voltage measurements, and with this to be able to process and get some resistance response for our measurements. And this time we didn't perform a cyclic load, but a displacement control load up to 1.5 millimeters, as we can observe here in this graphic. And from this model, I would like to mention and briefly focus on this equation of dt, where we define this based on some previous works, where we get a sort of elastic response, a sort of elastic estimation for each one of the cycles that we used later to try to evaluate the crack appearance in our samples. So for the first results here, we did some tests also without any load to see how was the conductivity of these samples and how the printing path would affect this conductivity. And we show, as we were expecting before, that the samples with the longitudinal direction, they were more, especially the paste, they were much more conductive in comparison to the perpendicular one for the paste as well. And this clearly because of the direction of the fibers that are following the direction of the electrodes, the placed electrodes. I also here I'm presenting some of the graphics for the paste longitudinal, paste transverse, and the mortar longitudinal, when we can clearly see rapidly increase in terms of fractional change in resistance for the longitudinal sample, especially for the beam, the paste, And with this, we can clearly see the crack initiation, the point where the fractional change increases rapidly. This is not so clear for the path with the transverse one. And also, an interesting, let's say, behavior was noticed for the mortar, where we got first a decrease and then an increase that we attributed mainly to the bridging effect of these fibers. Also because the sample was not, I must say that the mortar sample was not so well compacted and not so the printing quality was not so good as the paste, I would say. We also performed some graphics in terms of the fractional change in stress, and we noticed that the paste in the longitudinal direction was the one with the highest value of stress, followed by the mortar in the longitudinal direction and the paste in the perpendicular direction. And the fact of the longitudinal direction was the main one in terms of higher values for stress, was also due to the orientation of the fibers that were perpendicular to the applied load. this was not a notice, for example, for the perpendicular, for the transverse sample, for example. And these results clearly show the trend in terms of the variation of the conductive parameter and also the mechanical parameter that relates the elasticity variation in each one of the cycles. And we can notice also that the direction of the fiber can clearly affect the response in this sense too, since we can now clearly see that a bigger drop is noticed for the samples, both with the printing path following the long axis in the longitudinal direction. While in the perpendicular direction, this is not so clear with almost linear behavior, let's say. For the conclusion, just mention briefly that we could clearly see that the printing path clearly influenced both stress and also both sensitivity of the samples. And this was a quite interesting result that we were expecting too because of all the support from the literature. So it's also going, accompanying this sense. And also showing the promising possibilities of application of exploring different geometries in terms of self-sensing materials and 3D printing cementitious materials in general. So that's it for this presentation as well. I think it was faster than the other. Thank you.